Welcome to a presentation which I've entitled here Linear Fractional First Order Differential Equation. Let's see first of all what exactly are we talking about. But firstly, we must understand that this is part of our journey of dealing with differential equations reducible to separable variables. And I think this will be the last presentation in that kind of direction. So we shall say that a first order differential equation is fractional if it's given in this form. Like here, you've got dy dx equal to ax plus bx plus c over alpha x plus beta x plus delta. So equation of this form we're called linear fractional differential equation. And now what you must take note here, looking at the right hand side here, is that these constituting parts of this right hand side actually are linear equations, meaning equations of straight lines. And that is important to take note of. And then we note also that in the case that c here and the delta here are both equal to 0, we actually get an equation which is of homogeneous variables, which we have seen before. Like for example, we will get something like this. If c here and the delta are equal to 0, the equation is of this form, and you can verify that yourself that this is actually an equation of homogeneous variables x and y. So in general, this kind of equation will present us two cases. One of the cases is that the system of equations formed by the right hand side this way has got a unique solution, meaning the two lines actually intersect at a point. And the next case is when the two lines are parallel, meaning they have no point of intersection, and actually the system of equation above then will not have a solution. Now let's look closely at this case where the two lines forming this part of equation, you've got a point of intersection, and then suppose that the point of intersection is hk, and then by saying the point of intersection hk, we actually mean that the point hk satisfies the system of equation which is given here. So if we substitute h and k in the equation, we'll get the two equations being making 0. And then in that kind of situation, what we do, we consider changing variables from x to u by this kind of formulation. We set x equal to u plus h and y equals to v plus h, which actually here what we're doing, we're simply translating the system of equation to a new origin, which will be the point of intersection there. Then that will actually change and simplify our problem. So now considering that, what we've said, we should note that if we take dx here, we will see that dx is equal to du and the dy is equal to dv. And then in that case, substituting in this equation the variables x and y, we would get this expression. You substitute x and the y there in the two equations. Then simplifying that by removing the brackets and running terms, we get this kind of an expression. Now we should note that this part of the equation here is what we get there and is equal to 0, and likewise this one is what we get there and is equal to 0. So in this case, actually these parts are 0, and then what we're left with now, we're left with the equation of this form, which actually is the equation we've seen before, that this is an equation of homogeneous variables. In actually suggesting that from here onwards, we can treat this as an equation dv du of homogeneous variables and solve according to how the method we've used before. Then at that point, I think it is necessary that we look at an example of this type of equation where the two lines, you have got a point of intersection. So what we do then, we look at the system of equation, and obviously what we've seen, we've got to solve the system of equation, find the solution, which will be the point of intersection hk. And doing that, we see here that from equation 1, which is here, x is equal to minus half, and substituting in the next equation, we also get that y is equal to minus half. Then we've got to transform the variables by setting x equals to u minus half and the y equal to v minus half, and taking note also that dx is equal to du and the dy is equal to dv. I think you understand why this, because when you differentiate both sides here, the constants are going to differentiate to 0, like we've seen before. And then now substituting there and simplifying, you will see that dy dx, which is equal to this, and this is simple dv du, ends up after simplification being 2u over u plus 3v. And then it is at this point that you see that the equation you have here is the equation of homogeneous variable of this form, and then we can set our v to be uz, and then our dv du would be z plus u plus dz du. That is a familiar expression which you have seen before in terms of x and y. There we're just seeing it in terms of different variables which doesn't make any difference at all. And then we've got this equation simplified. So what we can do, we can just focus on these two, and then by focusing on those two, we get to the equation which is of this nature, which we can transform equivalently to be of this nature. And as you can see here, we are actually close to a situation where we can declare this equation of separate variable, because here you've got an expression of what? Of z alone. There you've got a u. I think you can now see, looking forward, that we are moving towards separating variables. But this only will make sense if you practiced this before in a similar situation. Otherwise, if you didn't, now all what I'm saying here wouldn't make any good sense. Now moving forward, we've grouped this expression and simplified, and then you get this kind of expression equals to u dz du. Again, there we can only focus on these extreme ends on the left and on the right. Then we get to a simple expression, which is this one. Then separating variables, doing your algebra here, you will see that you end up with this. Actually, what you see in this exercise is that your algebraic manipulation skills are going to be very, very important. Addition of rational fractions, manipulating them to get to the situation we've got several, all that needs a lot of good algebraic manipulation skills. Otherwise, without that, then you are going to have a challenge there. And now, when you've got this equation now, what you need to evoke is our knowledge of partial fractions. As you can see that the left-hand side here is a partial fraction of this form. I've left out dz there just to focus on the fraction, which actually needs us to split into its partial fractions this way. In that way, paving a way of later easily integrating both sides of this equation. So doing that, finding a and b, we have got that a is 2 over minus 2 over 5, and b is actually 9 there. Then once we've done that this way, we are now in a way we are closer to doing integration on both sides. What I encourage you to try to double check my calculations on this partial fractions, and double check my numbers, because that is important also. That will be part of a practice, just to recap on how to deal with partial fractions. Make sure that these numbers are correct. But according to my calculations, this is what I got, but I can't rule out the fact that there can be a numerical error there. But the process is very, very important. You must see what's provided. You do this, find your a and b, then you substitute back here. I think you'll be ready to integrate there. And now, integrating both sides, I'm not actually going to put an integral sign here. I'm just going to state that integrating both sides, what we get the following. We get here minus 2 over 5 multiplied by that line, and here you've got 3 line and that, and you should understand how this integral ended up ending here as minus 3 to that. Equals to, the right hand side is simply line of u plus c. And you can see here, this equation is dz du, which meaning our u is our independent variable, and I've added c here only on the side of the independent variable, what I've encouraged you to do before. And then what is left is to go back to the original variables x and y, and then you must just remember what we set u to be. If we set u to be, you had set u to be equals to, we've set x to be equals to u minus half, or u plus minus half. So making use substitute formula here, you see that u now is going to be x plus half. So doing that kind of change everywhere, we end up with the solution of the equation looking this way. And then at that point, we've actually completed our solution. I hope you have followed carefully the calculation, but if you're not sure, you can pause the video and start afresh again. But really, to do this, you must really pay attention to all the details and make sure that all the calculations which I didn't put here explicitly, you go through them so that you can familiarize yourself with what exactly is happening in this solving of these exercises. Now, moving forward, we have to practice with this kind of exercises. I've given you 5 of them there. You can go to text or recommended text and get some more of these and practice. Just try to solve all or most of these exercises until you feel you are familiar with this kind of work. Now we're going to move to the second case whereby the two lines are parallel. In this case, I'm not going to go into a lot of explanations with this one. What I'm going to do, I'm actually going to tackle this one immediately by means of example without going through any long explanation in this general form. In this case here now, we have to take note that alpha is equal to A and B is equal to beta. And when the equation looks that way, we should know that the lines which are involved here are parallel lines. So the system of equation we looked at before won't have a solution. So we don't have the chance of taking x equals to u plus h and y equal to v plus h. So then going to the example, we take this example which is exactly that. You can see A here and B, A and B in the numerator and denominator, they're equal. So if we've got that kind of situation, we then immediately set z, another helping variable there, to be equals to x plus y. And then when we do that, we notice that we can actually say y is equal to z minus x, and then dy, the expression for dy, will be of this form with dz dx minus 1 coming from here. Then that is what we're going to use moving forward. So then when we substitute in the equation there, we must get something like this. You can see that the right hand side dy dx is this, which we got the left hand side actually here, which is that, and the right hand side you simply replace this by z, that by z, we get something exactly like this. Then simplifying that, in our words, grouping, separating one on both sides of this equation, you can see I've written my 1 in terms of z minus 1, z over z minus 1, which is a 1. So I'm adding 1 on both sides here, and I get a 0 this side, plus that dz dx becomes dz dx. But this side, my 1, I decide to write it in this form as z minus 1 over z minus 1. Simplifying these two terms, I simply get a single term of this nature. And actually, I can see now that we are at a position where we can separate variables. So what we've seen actually in the other example, first of all, when we did the change, we arrived at homogeneous. Then from homogeneous, we move to separate variables. But now here, when lines are parallel, we do the substitution and we immediately land at an equation of separable variables. And then manipulating again, we have separated the variables this way. And then moving forward here, we split this fraction. I split it this way. You can see that you can't use partial fractions here, but what you can use, you can try long division. You will see that you land at an expression like this. But if you've got challenges like that, you can actually consult and see how you get that. But it's simple what we did here. We divided the numerator by the denominator in order to get the quotient, which is half, plus some remainder, which is which give us this rational expression. And at this point, we are ready to do direct integration on both sides. This here, which will give us s and that. So that's the reason why you've got this expression. So this will integrate to z over 2, and this to ln to minus 3 over 4 ln that plus the c. In other words, at that point, we're done with our integration. And then the simplest thing we'll do now is simple to substitute z, and we can see exactly what z is. There is z still sitting there. We can just come and plug in z, then we're back to the original variables, which gives us this kind of an expression. So at that point, we've completed our integration. Again, this kind of work, you need to pay attention to it and make sure that you can follow all the steps carefully, but you cannot learn to follow all these steps carefully without having some reasonable practice. So here are the exercises which you are going to use to consolidate this kind of work and make sure that you master the technique of solving this kind of equation. As you can see, this is all about the equations of separable variables, just taking equations in different forms and trying to transform them mathematically using our algebra to end up being equations of separable variables and solving them like we did initially with equations of separable variables. So I encourage you actually to go over this presentation maybe once more and really go slowly over it, look at the examples carefully, and attempt the exercise you are given carefully, and make yourself ready for this kind of work at any time you are given this kind of problem. You must be fluent in solving these kind of problems and continue with work without any challenges. In this case, the magic is practice, practice, and the practice. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Sugasfani Msipa.